All right, let's dive into it. We're about to tackle what is, without a doubt, the biggest question in all of science: the ultimate origin story. How did all of this, everything you see, from the tiniest particles to the biggest galaxies, how did it all come to be? For most of human history, this question was really for myths and philosophy. But over the last 100 years or so, science has pieced together this absolutely stunning, evidence-based picture of our cosmic beginning. The story starts 13.8 billion years ago with a single moment that, well, turned nothing into everything. Okay, first things first, let's get the biggest misconception out of the way right now. The Big Bang wasn't some kind of cosmic firecracker going off inside an empty room. No, no. It was the beginning of the room itself. It was the beginning of space, the beginning of time. It was all of space, everywhere, stretching out all at once. Now, this idea of a hot, dense beginning, it was absolutely revolutionary. But, as brilliant as the classic Big Bang model was, it left scientists with some seriously confusing puzzles. A few cosmic clues that just didn't quite line up. So here are the two big ones. First, you've got the horizon problem. See, when we look at the oldest light in the universe, its temperature is almost exactly the same everywhere. But how is that possible? Parts of the universe on opposite sides of the sky are so far apart that they could have never ever been in contact to even out their temperatures. It makes no sense. And then there's the flatness problem. Space-time seems to be perfectly flat on the grandest scales. I mean, that's like balancing a pencil on its tip for 13.8 billion years and it never falls over. It's just wildly, wildly improbable. So how do you solve these cosmic head-scratchers? Well, back in the late 70s, a physicist named Alan Guth came up with this absolutely breathtaking idea, a solution. He proposed a phase that happened before the hot Big Bang we all know about. He called it cosmic inflation. And the key word here is exponential. This wasn't the kind of slow, steady expansion that's happening today. Oh no. Inflation was something else entirely. It was a period of unbelievable, mind-bendingly fast growth. You can think of it as the ultimate cosmic growth spurt, the thing that set the stage for everything else. And when I say fast, I really mean it. This whole inflationary event was over in less than a trillionth of a trillionth of a trillionth of a second. I mean, it's a number so small, it's basically meaningless. But in that tiny, tiny instant, a piece of space smaller than a single atom ballooned out to a size larger than an entire supercluster of galaxies. It's really hard to wrap your brain around exponential growth, so let's try a little thought experiment. Imagine you're folding a piece of paper. After about 42 folds, that paper would be thick enough to reach the moon. But if you could fold it 90 times, that's roughly the number of doublings the universe went through. That single sheet of paper would be wider than the entire Virgo supercluster. That is the insane power of exponential expansion. And just like that, with this one incredible idea, the puzzles just vanish. The universe is so uniform because it all came from one tiny connected patch that was already smoothed out before it got stretched. And it's flat for the same reason an ant on the surface of a giant beach ball thinks the ground is flat. Inflation stretched our universe so incredibly much that to us it appears perfectly flat. It was just such an elegant solution. So what happened right after this incredible expansion slammed on the brakes? Well, the universe was about to enter its most chaotic, most formative period ever, the very first second of its life. When inflation ended, all of that energy that was driving it had to go somewhere. It got dumped back into space in a process called reheating. And this instantly created a searingly hot, incredibly dense soup of fundamental particles and energy. And this moment, right here, this is what we traditionally call the hot Big Bang. I mean, that first second was an absolute frenzy of activity. In just these impossibly small fractions of a second, the fundamental forces of nature we know today just sort of crystallized out one by one. Then, as the universe cooled just a tiny bit, quarks started glomming together, forming the very first protons and neutrons. And by the time a single second had passed, the ratio of these particles was locked in, setting the chemical recipe for the entire future cosmos. Now, here's something really cool about this early particle soup. There was this tiny but absolutely crucial imbalance. For every 1 billion particles of antimatter that were created, the universe also made 1,000,000,001 particles of matter. So after they all annihilated each other in a flush of energy, that tiny surplus, that one leftover particle in a billion, was all that was left. It's the reason we're here, the reason anything is here.
So for the next few minutes after that, the entire universe was basically one giant nuclear fusion reactor. The protons and neutrons that were just made started smashing into each other, fusing to form the first atomic nuclei. This process, it's called Big Bang nucleosynthesis, and it's what cooked up pretty much all the hydrogen and helium that exists in the universe today.
Okay, so the basic building blocks of matter are now in place, but for hundreds of thousands of years, the universe was still just this impenetrable fog. You literally could not have seen your hand in front of your face, because light itself was trapped.
And the reason was pretty simple. It was just still way too hot. You had electrons just zipping around freely, not attached to any nuclei. So a photon of light couldn't travel more than a few inches without just slamming into one of these free electrons and getting scattered. The whole universe was a glowing, opaque soup. But after 380,000 years of expanding and cooling, the universe finally dropped to about 3,000 Kelvin. And at that temperature, those freewheeling electrons could finally be captured by the atomic nuclei, forming the first stable neutral atoms. And just like that, suddenly, the fog cleared. The universe became transparent. And those photons, the ones that were set free in that exact instant, have been traveling across the expanding universe ever since. We can still see that ancient light today. We call it the cosmic microwave background, or CMB, and it is, without a doubt, the single most powerful piece of evidence for this entire story. It's literally a baby picture of our universe.
Now, this whole story, it's our best scientific picture of how it all began. But the search for answers doesn't stop here. In fact, the idea of inflation kind of blows the doors open to a whole new world of even bigger questions about what might have come before and what could lie beyond our own cosmic horizon. And this is where things get really, really wild. Some theories suggest that inflation never truly stopped everywhere, that maybe it's still going on, constantly spawning countless new bubble universes, just like ours in this vast multiverse. Other ideas propose that our universe was born from the collision of these higher dimensional surfaces called branes, and some even think our universe might be cyclical, that it's just the latest in an endless series of big bangs and big crunches.
All of this leads us to the ultimate question, a question that was pure science fiction just a few decades ago, but is now a really serious area of scientific research. It pushes right up against the very limits of what we can know and what we can even imagine. Is our universe the only one? Is everything we see truly everything there is?